So first, let's go and compare an octahedral geometry versus a tetrahedral geometry. And we need to try to analyze the shapes of these. If we analyze the strong interactions in an octahedral complex, we would have a strong interaction between the transition metal and the dz squared orbital and the dx squared minus y squared orbital. Our weaker interactions are going to be between the transition metal and the dxy, the dyz, and the dxz. We drew pictures of this the other day in lecture. We can look at a tetrahedral complex in the same way, where we need to try to determine our strong interactions and our weak interactions, because the type of interaction is going to dictate our energies of our d orbitals. If you draw a tetrahedron, typically you have your transition metal center and you have your 4 ligands around here. And we typically draw them just like this. In this drawing, I think we would imply that the z-axis goes straight up and down like this. But remember when I talked about all the bonding theories of transition metal complexes? We talked about something called molecular orbital theory, which uses group theory. There's mathematical proofs that are set up to analyze these orbital interactions. And the way they set this up is they do not define the z-axis pointing straight up and down like this. They actually define the z-axis to bisect this ligand metal bond. This is going to influence how the ligands interact with each of the d orbitals. The best way to visualize this is to draw the tetrahedron inside of a cube. So if we draw a cube and we assume that the z-axis goes straight up and down through the center of this cube, and we place our transition metal right in the center of that cube, the ligands that we would draw would be 2 ligands down here, which would form this 109.5 degree angle. And then there would be 2 ligands on these ends of the cube right here, forming another 109.5 angle. This will give us our tetrahedral molecule the way that a group theorist would analyze this. An easier way to do this would be to look straight down the top through this point of the cube. So if we looked at a top view, this is really going to illustrate our strong and our weak interactions in terms of the orbitals that are going to overlap the best with this. So if we assume our transition metal is right here in the center, and the z-axis comes straight out of the page from that center, we're going to have 2 ligands here that are above the plane, and 2 ligands here that are below that plane. So if a dz squared interacted with these ligands, it's going to be, this would be like the top of that barbell lobe of the dz squared. It's not going to interact very well with those ligands. If we looked at these axes right here and we said this is the x and this is the y axis, and I would draw on here the dx squared minus y squared orbitals, the lobes would look like this. So here's how the dx squared minus y squared ligands would interact with the transition metal. Or the transition metal dx squared minus y squared orbitals. But if I would go back and I would draw the dxy orbitals, they would point like this. And I've kind of shown them here in pink. And that interaction right here is going to be much stronger than the interaction with the dx squared minus y squared. And when I start to draw these ligands in this fashion, you can kind of see that this is why we typically separate these orbitals and draw them one at a time, because it starts to get really complex in there. But this is what those ligands are seeing when they look at this transition metal. So what I'm trying to emphasize here is that in a tetrahedral molecule, the strong interactions are going to be between the transition metal and the dxy, dxz, and the dyz. And the weak interactions are going to be between the transition metal and the dx squared minus y squared and the dz squared. So this is going to influence the relative energies and the splitting of those d orbitals. So if this is our energy scale right here, in an octahedral case, we have the T2g and the Eg orbitals separated by what we would call delta O. In this case, the T2gs are the weak interaction, and the Egs are the strong interaction. The opposite case is true for a tetrahedral molecule. Our strong interaction are going to be the dxy, xz, and yz. So here, our triply degenerate orbitals are going to be the ones that have the highest energy, and our doubly degenerate orbitals are going to be the ones with the lower energy. We give different names to the triply degenerate and doubly degenerate orbitals, or we give different symbols for a tetrahedron versus an octahedron. In a tetrahedral molecule, the triply degenerate are simply abbreviated as a T2, and the doubly degenerate are simply abbreviated with an E. This gives a delta T, which would be the difference between the E set and T2G set of d orbitals. One thing that you should notice here, and again I should draw in that the E set of orbitals are the weak interaction, and the T2 set of orbitals is your strong interaction. One thing that we can note, and we can prove this mathematically, is that delta T is going to be much smaller than delta O. There's actually a mathematical relationship that says delta T is equal to 4/9 the delta O. So we can say that delta T is much smaller than delta O. This is going to have a consequence on the magnetism, and it's going to impact this very much so. So if we can say that delta T is much smaller than delta O, we can say that all tetrahedral complexes are high spin. So when we're looking at the magnetism, you're going to have high spin for all your tetrahedral complexes.